So in today's section, we're going to talk about another method that's going to help us solve some integration problems, which is trigonometric substitution. We use trigonometric substitution when we have these square roots with either a difference of two squares or a sum of two squares in the square root. So let's start with the first square root that we have. If I have a square root with a squared minus x squared inside of it. So using the methods that we've learned before, we can't integrate it directly. So here we need to find another method that's going to help us integrate these kind of roots. So here we're going to do some sort of substitution, but the substitution will include something with trig functions. So like sine, secant, tan, and so on. So the first step, let's identify the domain for this square root. So if you find the domain, you'll find that your x would be between negative a and a. If you divide by a, you're going to get that x over a is between negative 1 and 1. Now, if you take sine of x in general, you know that the range of sine of x is between negative 1 and 1. And this is where, when you have like your theta to be between negative pi over 2 and pi over 2. So we can say that sine of theta is x over 2. Sorry, this is x over a. Yeah, because any theta between negative pi over 2 and pi over 2 would give me negative 1 over 1. And x over a is just negative 1 over 1. So we're going to identify this to be this. You'll see why this is useful in a bit. Okay, so the first step when you have an integral including this root, you want to make sure that you can't integrate it in an easier way, like using regular substitution, using, I don't know, like a formula that you already know. So if that's the case, you use the regular method that you've learned before and integrate easily. But if none of them work, here we need to do a trig substitution. So when you have a squared minus x squared, you're always going to use the substitution of x is equal to a sine of theta. If you do dx, this is just a cosine d theta, and we're going to use this identity. Cosine squared is equal to 1 minus sine squared. So the whole point here is I want to get rid of this negative. Because if you have a negative or a plus inside of your square root, you can't distribute the root and simplify. So I want to try to make this into one thing or a product of things so I can just distribute the root and simplify. So let's see why this works. If you have this square root that you're going to start with, and I'm using this substitution. Once you plug it in instead of x, you're going to get a squared minus a squared sine squared. Then you're going to take a squared as a common factor, and you'll get 1 minus sine squared. But we know that 1 minus sine squared is just cosine squared. So once you plug it there, you're going to get the square root of a squared cosine squared. So that's a multiplication. You can split the root and take the square root for each one. So you're going to get a cosine with the absolute value. But since cosine is always positive when we have theta between negative pi over 2 and pi over 2. So this is just a cosine of theta. Okay, now once you go from the square root to something easy, now you want to simplify your integrand and integrate using previous methods easily. Okay, now since we're doing a substitution, if you start with the variable x, your answer should end with a variable x. So sometimes it's kind of difficult to just plug in the substitution back in because you're going to get something new in the answer. You'll see in a bit how. So here, we're going to use a right angle triangle. Since we have trig functions, we know that there's a relation between a right angle triangle and its ratios and these trig functions. So here we know that sine of theta is just x over a from this substitution. If you build a triangle, a right angle triangle, you know that sine is opposite over hypotenuse, so opposite over hypotenuse, and then you use the Pythagorean theorem to find the missing side. And here theta is between negative pi over 2 and pi over 2. Also, if you want to find the value of theta by itself, because sometimes in the final answer, you'll get theta by itself. So here, if you apply sine inverse to both sides, you'll get that theta is just sine inverse x over a. Okay, so a bunch of steps that does not make a lot of sense. So let's do an example. So let's start with number 1. I have the square root of 4 minus x squared. If you try any other method, you're not going to be able to integrate it easily. So here we need to use trig sub. Since I have 4 minus x squared, my a is just 2. So I'll take the substitution of 2 sine of theta. So now dx is 2 cosine d of theta, and let's plug everything back in. So I have the square root of 4 minus 2 sine of theta all squared times 2 cosine of theta d of theta. Now let's simplify. I'm going to have the square root of 4 minus 4 sine squared, 2 cosine d of theta. Okay, now this, if you simplify it, you're going to get 2 cosine. So I'm going to have 2 cosine times 2 cosine. So that's 4 cosine squared d of theta. Now, if you remember from the previous video, when I have cosine squared, I need to use an identity. 1/2 plus 1/2 cosine 2 theta. And this we can integrate quite easy. So this is 2 theta plus 2 sine 2 theta over 2. Again, if you want to integrate cosine of 2 theta when you have like an extra number here, you can either use a u substitution or just divide by the coefficient of what's inside, plus c. Now if you see, I started with an integral in terms of x, but I ended with an integral with an answer in terms of theta. So I need to find an answer in terms of x. So to do that, we're going to use either the right angle triangle, or if we have theta, I'm just going to write it as sine inverse. So here, since I have a theta, this is just 2 sine inverse x over a, which is 2. Now here, I have sine of 2 theta, but if you build a triangle here, using sine of theta is equal to x over 2, you have the triangle in terms of theta, not 2 theta. So here, we need to use another identity. For sine 2 theta, this is just 2 sine of theta cosine of theta. And now we're going to use the triangle here to find the values of sine and cosine. So here, cosine is adjacent over hypotenuse. And I already know sine, so now you just plug it back in. And this would be the final answer. So it's not too bad, right? It's just a lot of steps. So for the second example, we have the same square root, but we have an x in the denominator. Again, if you check, you can't use a u substitution, or like we don't have a formula that's going to integrate easily. So we're going to use the same substitution. X is 2 sine theta. And now, if you plug it back in, now we know that this square root got me 2 cosine over 2 sine times 2 cosine of theta d of theta. So we're going to get the integral of 2 cosine squared of theta over sine of theta d of theta. Okay, so now when you look at this integral, you're gonna think, oh, maybe a u substitution would work. But if you either take a u substitution of sine or cosine, you're not gonna be able to simplify it fully. You're gonna have an extra term with a theta even after a u substitution. So here we can think about, oh, cosine squared is 1 minus sine squared. So let's see if that would help. And we know that we can distribute the denominator. So I'm going to have 2, the integral of 1 over sine, which is cosecant, d of theta, minus 2. And then sine squared over sine, this is just sine of theta, d of theta. And now this is these are just antiderivatives. And now we're going to build a triangle again, which is the same exact triangle. Now cosecant is 1 over sine. And we know that sine from here is x over 2. So this is going to be 2 over x plus cotan is 1 over tan, and tan is opposite over adjacent. So this is going to be the square root of 4 minus x squared over x plus 2 plus c, and so on. Okay. Now let's try this example. What if I have a square root with a squared minus x squared, but I have an extra coefficient with my x squared? So here, even though that if I use a substitution of like, oh, a sine of theta, that would work, but the problem is I want to use this identity to simplify and get rid of the square root, because I want to turn something from a difference to a multiplication, and I can get rid of the square root. So I need to have a 1 as a coefficient of sine squared. So here the trick is, let's rewrite what we have as the square root of 9 minus, now 16 is just 4 squared, so I can write it as 4x all squared. And now for the substitution, instead of taking x, I'll take 4x to be the regular substitution, which is a sine of theta, and here a is 3, so 3 sine of theta. If you find the derivative, same exact steps, and let's try and put it back in. So now I have the square root of 9 minus 4x squared dx. Now 4x is just 3 sine of theta multiplied. Now here, since I have an extra 4 and I only want to substitute my d of x, I need to divide by 4. So dx is just 3 over 4 cosine of theta d of theta. And now this whole thing would turn into 3 cosine. And we're going to have 9 over 4, the integral of cosine squared theta d of theta. And you can do the same exact step as question number 1. Okay, so this is when we have a squared minus x squared. Now what happens if I have a squared plus x squared? Okay, so here the domain for this root is just all numbers, because no matter what value of x you plug in, you're going to get something positive. So x is just the domain of that is just the whole real line. Now, since the domain is just the whole real line, which means like the ranges that I'm getting is all real numbers. So the trig function that has a range of all real numbers is either tan or cotan. So you can use either tan or cotan as your substitution here, but it's more common to use tan. So again, before integrating, double check that you can't use a regular u substitution or a quicker way to evaluate it. If you can't, go straight to the trig substitution. So when you have a plus sign here, you're gonna need a tan of theta, and we're gonna need this identity. So the reason why we chose tan like the other reason for choosing tan is because this identity has a plus here, and I have a plus here. So that's why this plus would work. Now again, if you plug it back here, you're gonna get a squared 1 plus tan squared, which is your secant squared. And now if you take the square root, you're gonna get a secant theta. Again, we simplify and we integrate. And now if we want to plug in the answer in terms of x back in, we're gonna use the inverse to get theta. We're gonna use this triangle to get any trig function that we want. Now tan of theta from here is just x over a, and this is by Pythagorean, and we have this to be my theta. So let's try it. If we have 1 over the square root of 9 plus x squared, if you use a u substitution, that's not going to work, so a trig sub. If you find the derivative, and now let's plug it back in. And now if you simplify, this whole thing is going to be 3 secant theta d of theta. So we're integrating secant theta by itself, but we know that this is just ln of secant theta plus tan of theta plus c. Now, if you want to get the answer in terms of x, you build a triangle with the substitution that you started with. So here tan of theta is x over 3. So opposite over adjacent, then Pythagorean. And now let's see. Secant is 1 over cosine. Cosine is adjacent over hypotenuse. So that's hypotenuse over adjacent, plus tan is just x over 3 plus c. So we started with an integral in terms of x, we ended with an answer in terms of x, we're done. Okay, now for the second example, we're gonna do the same exact thing. Since a regular u sub would not work, I need to take my x to be 2 tan of theta and integrate, and then plug it and differentiate and plug it back in. So here, if I got x cubed inside of the square root and x squared on the outside, a u sub would work. So now let's put it back in. Instead of x, we have 2 tan of theta. Okay, so let's see. Now we got the square root of 8 tan cubed of theta, and then this thing is going to turn into 2 secant theta. So we're going to have another 4 secant times secant squared. So this is secant theta and d of theta. So now we have 32, the integral of tan cubed theta, secant theta, d theta. And now this is a trick that we're gonna use the previous video, like the way that we did, we're gonna use it here. So here, if you think about it, if you take your u sub to be secant theta, your du is gonna be secant tan, right? So if you take one of these tans with one of these secants, you're gonna get tan of theta squared, secant squared of theta times tan secant theta, d of theta. Now this is just du. This is my u. And we know that tan squared is just secant squared minus 1. So I can just put it in terms of u. So this is 32, the square root, not the square root, the integral of u squared minus 1 times u squared times du. you distribute and integrate and do the regular substitution by plugging x back in using the triangle. Okay, so the last thing that we're going to talk about today is integrating when we have a square root of x squared minus a squared. So here, the substitution that we're going to use is secant theta. Because if you look at the identity, I have a secant theta minus 1 here. So since I have a minus here, I need to have an identity with a minus there. Now, if you plug it back into the square root, you're going to get a squared tan squared theta, the absolute value of a tan theta. So now here, I can't say that this is just a tan of theta, because for different values of x, or like a, we're going to have something positive and something negative. So here, if x is bigger than a, we're going to get something positive. If x is less than negative a, we're going to get something negative. Because if you take the domain here, you're going to have this domain. So we have two parts. Okay, now the same exact process, nothing changes here. The only thing difference is when you have the triangle, you're going to have two cases. One with positive x bigger than a, and one with x less than negative a. So it all depends. Like here in the question, it's given, so you know which triangle you're going to use. And we have these values of theta. So let's try this example. Since x is bigger than 2, I know I'm going to use this triangle with this domain for theta. So here x is just 2 secant theta. So dx is just 2 secant tan. Let's plug it back in. Once you simplify, once you simplify the denominator, you're going to get 2 tan. So I'm going to cancel the 2 tan with this. So I have the integral of secant theta, d of theta, which is just ln of secant tan plus c. Since x is bigger than 2, I have a triangle in the first quadrant, which is perfect because now I have secant theta is x over 2 from the substitution. And now secant is 1 over cosine, so this is going to be my hypotenuse. This is the adjacent, and this is x squared minus 4. Since I want tan, tan is opposite over adjacent, and I already know that secant is just x over 2 plus c. So technically that's it for all of these substitutions. You have these suggested problems, and you can do these problems from Lumen. So like, keep in mind that the main idea with these substitutions is all about these identities. So if you're able to use these identities somehow to relate, like, oh, if I have a negative one here, I need to have a negative with here. If you, like, no matter where you take the 1 here, you're not going to get here, like here I have a negative a number. So here, no matter where you take the 1, you're not going to be able to get something minus 1. But here you can easily do it by taking a 1 here. So that's why when you have a square root of this kind, you only can use this identity, and so on for the other cases. So if you have any questions, please let me know and email me, and good luck with everything.